Okay, so good afternoon, ladies and gentlemen. Thanks again for tuning in to another Risk Institute online session. Today, we're especially fortunate to have with us Dr. Mark Bankhead, a friend of the Institute and expert in mathematical models of chemical behaviour, and is working at the National Nuclear Laboratory, to speak to us a little bit about digital twins in nuclear. So the presentation will be around 45 minutes with around 20 to 30 minutes of Q&A. Please could you make sure that your mics are muted and leave any questions in the chat, or virtually raise your hand once the session is over, and I'll select them on behalf of Dr. Bankhead. So he'll be talking to us today about digital transformation, digital twin technology, in particular an exciting topic within the nuclear industry. Digital twins have the potential to address many of the challenges that impact on nuclear's cost effectiveness, including siloed working, loss of fidelity of information during handover, and a digitally aware culture that embraces the benefits of digital and drives changes across business practices. So in this talk today, we'll explore some of the motivations behind digital transformation, look at some of the challenges and solutions they have delivered under the BEIS funded Nuclear Innovation Programme, Project Faith, and he'll share some of the successes and appreciations of the gaps in the sector. So Dr. Mark Bankhead is a scientist with over 19 years of experience working in the nuclear industry. His work involves development of complex mathematical models, as I said. He's a technical lead with experience of leading several multidisciplinary research projects, ranging from modeling the behavior of atoms through to understanding the impact of chemistry on process behavior. And since 2006, he's led several projects developing the scientific computing for the National Nuclear Laboratory. And this has led him to play an active role in digital for Nuclear Industry Association and the UK's Nuclear Innovation Programme. So without further ado, if you'd like to share your slides, Mark, and we can begin.
Yeah, sure. I was also going to comment as well. Hopefully everyone can hear me okay. I was also going to comment, I don't move very much these days because the photograph I've used on the picture there is almost identical to this, what you see now, apart from the slightly different camera angle. So just give me a second to find
no problem
the sharing button, which has disappeared. What am I doing?
No problem at all. I mean, it's the big green one.
Where's the sharing option?
It's normally on the bottom here.
Oh yeah.
Share screen with the green button.
It's a share screen. That's it. Found it. Sorry. Okay, here we go. Good afternoon, everybody. Let's just click on the presenter view. Everyone got that?
If you'd like to switch over the displays, I think it's showing the second view. It says in the top left there, use, yeah, there you go.
This better?
Perfect, we can see it.
Awesome. Thanks everyone for joining us. I'm Dr. Mark Bankhead from the National Nuclear Laboratory. I'll skip on. Many of you are probably aware of the National Nuclear Laboratory, but I'll give you a bit of an overview anyway. So NNL is the UK's National Nuclear Laboratory. We operate on an autonomous commercial basis. We're fully owned by the UK government, and we have three roles which have been given to us by government. Number one is to act as a UK technical advisor. Number two is to act as a commercial business where we deliver R&D solutions to a range of customers, both within government and also within the nuclear industry in the UK and beyond as well. And then the third of our missions is to undertake what we call national strategic technical work, which is largely aimed at things like maintaining skills and capability for the UK, undertaking sort of critical R&D projects that are needed to support the UK's infrastructure that's underpinned by nuclear energy. To deliver this, we operate a number of world-leading facilities, including sort of active cells for working with radioactive materials, through to computation, which is probably more my area of expertise. And then, of course, we do world-class science because everyone does that, don't we? So, Today I'm going to talk about digital and digital in nuclear specifically. So why digital in nuclear? Well, number one, we've got some hard targets to go at. So we think that innovative nuclear power technology is needed to meet the government's commitment to have achieved net zero in terms of carbon emissions by 2050. You know, there's definitely a role for nuclear there. How big or how small of it is needs to be established. But we've seen for the first time in generations, new plants under construction with EDF. One is already under construction. The second is, well, that's also under construction now, actually. Large nuclear plants. We have other reactor technologies in the pipeline as well, from small modular reactors to advanced modular reactors. To meet those opportunities for nuclear, the nuclear sector deal was drawn up between the UK government and the UK nuclear industry. And there we set out a couple of objectives which are really important for digital. And these are, by 2030, we wanted to deliver, we were committed to delivering a cost savings of 30% on new builds for nuclear plants, and overall achieve a 20% cost reduction in forecast decommissioning activities for cleaning up the legacy nuclear plants and waste that have existed from the previous generation of nuclear plant that the UK has operated. We also want to create a more competitive supply chain and grow that by 2030. So it's worth £2 billion to the UK economy through international contract wins. And if we're going to meet those targets, the nuclear industry, to be blunt, needs to do things a lot better than it has done in the past. Here are some challenges that it faces. Number one, siloed working. Often you hear nuclear people talk about siloed working. Siloed working was actually created as a positive thing back in the day. It was a means of controlling information by clearly identifying where the information owners were within a business. But today that's a problem, because through various things such as retirements, people moving on in the business change, the old networks of information sharing have long since disappeared or ground down, so they don't really work effectively anymore. So what we're left with is a situation where we have pieces of information which are fragmented across organizations, particularly where we've got larger organizations, but also not only within the organizations such as Sellafield Limited or NDA, but outside of them as well, because many of the old parts of the UK nuclear industry are now owned by, for example, large American corporations, for example, and those guys hold on to critical pieces of information. So the nuclear industry in the UK has become very, very fragmented as a result of that, and information is very fragmented as well. Another challenge that we face, and this isn't actually just a nuclear problem, but because we've got so much to do, it's something that's really important for us, and that's loss of fidelity during handover of information. What that results is project slippages and cost overruns. And I'm actually going to talk a bit about that in my talk today and give an example of basically how simple mistake in a project can actually result in a big cost overrun. Put it bluntly, the nuclear industry's got a lot to do. It needs to do better than everybody else at avoiding these issues if we're going to achieve that 30% cost savings on new builds and 20% cost savings on decommissioning. The third point, which links back to the discussion I made on the first point, is collaborative working. Because the nuclear industry in the UK is now very fragmented, we're not going to see a large corporate entity where everyone's merged together as one big happy family anymore, because that would just be too complicated and expensive to create. So what we'll end up with is a need to collaborate across organizations. And to do that, we need to share data in a secure way. And that will help us also address the issues around siloed working. Okay. So now I'm going to talk a bit about what is digital. So I gave this presentation at the Institute of Physics a few weeks ago, couple of months ago actually now, and I've sort of cut down a little bit about this, but I thought I'd leave some of this discussion in there around basically what is digital, what I think digital is about, and I've toned down a little bit about a few of the rants I have about the IT sector in particular on this one, but we can always revisit that in the Q&A session later on. So what's digital about? Well, digital is about going from the bottom to the top. So we have data and we want to make decisions based on that data. And quite simply, to do that, we need to use digital technology. So informed decisions only come from knowledge. Knowledge comes from certainty, which, you know, we're all scientists and mathematicians here, so we know that we can't actually get to certainty directly. We can, however, calculate uncertainty by using computer models, simulation is the tools that we have available, well established for many decades. This requires digital capability, and then the digital capability is the bridge to the actual underpinning data. And what drives the informed decision is the acquisition of data. And we can think about it as across the life cycle of an asset and across the different scales that are representative for the asset, for that asset, we can acquire different types of data. So for example, from construction, we can get information on the design of the building. From, you know, today we capture it in something like building information modeling, but in the past we had often paper-based drawings and other sorts of information. Information on specific unit operations within the facility, such as the core of a nuclear reactor or the evaporator in a reprocessing plant. Breaking it down again, we can look at, for example, the materials that form that component in the reactor or whatever, or another form of nuclear plant, and we can acquire various different data on that, such as the temperature profile, stress and strain, etc. And then we can go down a level further, which is more the mechanistic understanding of those materials. So fundamental property data, physical property data about the materials that form that asset. These are the sources of data that's available to us to support our informed decisions. What we want to create in nuclear is a digital ecosystem or common modeling environment, and I'll revisit common modeling environment later on that, where we can actually represent in a digital way all of the components of the assets and all of the information that forms within it, and actually use the digital ecosystem to explore various different aspects of that design. For example, how the various different unit operations link up to deliver the overall performance or systems engineering of the asset. That'd be one example. How the material properties and material degradation of, say, fuel in a reactor impacts on the performance of the reactor, the lifetime of the fuel, and the burnup that can be achieved. There's numerous examples of that. And what we want to be able to do is to do this all digitally. Now, today we can do that, but only individually. So at the moment, we have all the different bits. We have models of plants, we have models of unit operations, we've got models of components in the reactor, we've got models of subcomponents in the reactor. What we don't have is the ability for those individual models to talk to each other. So a lot of the information that's passed between the different models to give informed decisions actually takes place from a model to a human, to a human, to a model. And that process is extremely inefficient, and it results in a loss of fidelity of information when you make that step. And what we're trying to create is and through digital twins and digital common modeling environments, is that digital ecosystem that allows that to happen with a degree of automation to reduce the loss of information that occurs over the handover step. So what's the need? You can drive it down from the top. So from the top down, you've got increased value, lower costs. That's the nuclear sector deal objectives. We want better optimized systems. We want increased certainty and better assurance over the operation of our facilities. What we need from digital is high fidelity simulation, numerical quantification of uncertainty, And together that will make decision makers better informed. Okay. So this is a bit where I sort of go a little bit off piece in terms of, so what is digital transformation? Well, digital transformation for me means doing things differently. It doesn't mean simply enhancing what we already have. I'm going to give a couple of examples of this, because in this world that we live in, we talk about digital transformation, and I hear a lot in the nuclear industry about what we're doing today. We're doing a video stream over Zoom, which is a conference. And one of the messages I've heard is that video conferencing has transformed the way we're operating in a post-COVID world. Is that true? Well, actually, really, nothing significantly has changed about, for example, the way we run meetings. It's meant that we have to travel a little bit less, which might have had some personal benefits to us as individuals. But in many ways, actually, doing meetings over Zoom actually degrades the experience that you have in the meeting, because you lose a lot of the sort of one-on-one interactions that can occur outside the meeting. As a speaker, I find it a very unrewarding experience to often come to conferences and give talks, because I don't get to meet anybody when I do it. I just get to talk at people, or rather talk at the screen. And so I don't think that's actually transformational. I think it's been a positive thing. It's allowed businesses to operate during COVID, but there's a lot more needs to be done with digital technology before electronic technology like this will actually replace the experience of meetings, particularly going in collaboration. I don't think that's transformational. There's also a risk, and you see this a lot, in the IT sector, we're notorious for this, is we misadopt digitalization simply to become buzzword compliant. So you hear that the term digital twins bandied about now in software companies, from the large organizations such as Microsoft through to Siemens. You know, to Siemens, a digital twin is something they actually tried to trademark, the term digital twin. To Microsoft, it's just a language, a programming language. And they said, this is Microsoft digital twins. There's all different types of technological solutions being basically built around the buzzwords of digital twins, common modeling environments, BIM, etc. And there's a risk that, you know, we'll simply adopt the wrong solutions simply because we believe the hype, so to speak. So if Microsoft sell a digital twin solution, there's a risk the nuclear industry could adopt that solution thinking, this is going to be great, this is going to do everything that we want. And in reality, it isn't actually got the capability to do what we want, and we'll be disappointed. Perfect example of that is big data. So we saw this many years ago. A lot of tech companies were pushing big data solutions. And what big data actually meant as a term originally was that we're able to make decisions that are not limited by our ability to acquire and process data. There's absolutely no way that the technology we have on Earth today can do that for any business, really, to be blunt. It's not achievable. We've got technologies that can, you know, Internet of Things technologies that can do some things, and we can get some information from it. They'll make an improvement on the business, but by no means are all decisions, decisions going to be not limited by our ability to process information. So we have to be wary of this when we adopt digital technologies and not expect it to come in and solve every problem straight away. Okay, so where do we go next with digital? So these are my 3 challenges again: siloed working, loss of fidelity, doing handover of information, and collaborative working. So to look at siloed working, what we probably would like to do is to develop some case studies where we can demonstrate the value and innovation of sharing data. And that would help to demonstrate where we can use digital technologies to start to address this. Loss of fidelity during handover of information. What we really want is some test projects where we can, perhaps doing a simple R&D project, which involves role of intelligent clients and subcontractors where we're exchanging data between different parties, and we can see how digital would fit into that sort of world. Collaborative working. Again, what we need is a multi-partner collaborative R&D program that involves data information sharing. And if you have all these things together, we can start to bring digital into those projects and actually start demonstrating where we can start use digital technology to address those objectives. So that's exactly what we did. So we came up with Project FAITH, which stands for Fuel Assemblies Incorporating Thermal Hydraulics. So this was a project that's just recently come to an end. It was a £5.1 million project funded by BEIS under the Advanced Manufacturing Materials Programme, part of 40 million they allocated to this in the last comprehensive spending review round. There was 4 projects in the phase that we were, FAITH was in, and there was 5 projects under phase 2B. That was also funded as well. It formally completed in September 21. Well, it is due to formally complete in September 2021. That was extended a little bit by COVID and the impact on deliverables. So FAITH was a partnership of GE Hitachi, Cameled, NNL, Jacobs, Fraser Nash, University of Liverpool involved, NEMRC, and some SMEs as well. What it was about was effectively building test rigs for thermal hydraulics experimental science. And there was 3 sort of main drivers and benefits that we're hoping to get out of this project. Number 1 was to demonstrate, and this is the major motivator for Project FAITH, was to demonstrate off-site modular manufacture. So there we had Cameled as a partner. They were bringing their experience from shipbuilding. The idea was to design test rigs for looking at the flow within sodium-cooled fast reactor test assembly. The plan was to build eventually 2 rigs. We got to the point of building 1 of them, designing the second. The first one used water reserve working fluid, and the second one was planned to use sodium, which hopefully we'll get to do in some time in the future. And there it was about technology transfer and upskilling skills for nuclear, transferring nuclear skills into Cameled so they can bring their shipbuilding experience into nuclear. Second part was the thermal hydraulic science itself. So we recognize, particularly within the National Nuclear Laboratory, that almost all of the experience that we would have had back in the days when nuclear was really big in the UK and not present in the National Nuclear Laboratory and not great in the supply chain either. So this was a great opportunity to start to use this project to rebuild some of those skills. That involved, for example, we did a master's project with Bruno Merck at University of Liverpool to train one of our staff in thermal hydraulics and nuclear engineering. We got to work with industry on advanced modular reactor designs and share information on thermal hydraulic science. We're also spinning off that into PhD projects now. And then the third part of it was digital. And what we wanted to do with digital was to start to develop digital tools to see, well, how could we get this all to fit together? How could we go from the simple rig, which is the water rig, to the sodium rig as quickly and as cheaply as possible, and using digital technology to remove some of the bottlenecks and issues that could arise during that project, and demonstrate digital twins across the life cycle of the asset as part of that. So just a bit of a summary of the Project FAITH motivations. So nuclear expertise, that involved NNL working with Cameled and GE Hitachi. Cameled brought in the shipbuilding and modular manufacturing approach. We wanted to deliver that cost-effective solution for off-site modular manufacturing, modular methodology, and digital technology. That's our key themes again. So, I mean, the main thing is that, you know, for our modular manufacturers, it's easy to claim, hard to do. And that's what we wanted to try to demonstrate with this project, and how we can apply digital to learn and to deliver more effectively. One of the benefits of doing this on Project FAITH is it's a small project. The rigs are very simple. The aims are very simple. So we can try to demonstrate a whole aspect of different technologies, digital technologies and other technologies in Project FAITH. And what that gives us is the ability to have that steep learning curve So we can actually, what we want to do is actually, give us a real challenge so we learn quickly on a small scale, so we can then scale that up to a much bigger scale in the future. So that was the idea, going from the simple test rig of the water loop into the more complex, and from operational safety perspective, rig, which will be working with liquid sodium. Okay, so looking at FAIF as a whole, or this would apply to any project actually, not just a nuclear project, you look at the various different stages that project is broken down into, and then we're going to use this model as basically a basis for understanding where we start to fit in digital technologies against it. So what we do, starting from left to right, we do design, construction, operation, maintenance, and decommissioning. To do this effectively, however, what we need to do is plan from right to left, which is we plan for decommissioning, we have an assured outcome in mind of decommissioning plan. We want to understand the maintenance and operational aspects of the asset, so we can reduce the operational cost and get confidence. From an operational point of view, we want to make sure that the asset does what it's intended to do to maximize the return on investment and ensure the operation is safe in its operation. From construction, we want to avoid rework. We want to exploit the supply chain, and we again want to reduce the costs by up to 30%, again, meeting those objectives initially. And from a design point of view, we want to have an optimal solution, and we understand the safety issues on. And that's very important, is that from a client point of view, we want to drive this from right to left. And that's this is the model that we've used to start to develop the digital technologies upon, and to start to address these kind of bigger questions in nuclear. So the ultimate goal that we set ourselves was to move to what we call a common modeling environment, which is an extension of a concept used in building information modeling, which they call a common data environment. Basically, the big difference between them is that you can also model and predict performance of the asset from within the single environment. And the problem we want to solve is this picture on the left-hand side shows basically how information, a simplified description about information passes today. So basically in a project, you've got various different roles. All information is transmitted between individuals by basically binary interactions. So a scientist sends information to a client who then has to interpret what the scientist is talking about, basically. The scientist sends a specification to the supplier who goes and builds their instrument that they need to do their work, etc. The project manager tries to talk to everybody to try to understand what's going on. The process is, despite all the organizational structures you put into businesses, the processes of information sharing can be extremely chaotic. And this is true across so many different businesses. What we want from a common modeling environment is to create a centralized asset of digital information that everybody interacts with. So when a scientist sends a specification to a client, what happens is the scientist interacts with the common modeling environment, and the client interacts with the common modeling environment to get the information that they need to design the experiment that the scientist wants to do their work. That eliminates some of the bottlenecks and issues that can occur in the transfer of information. And of course, the peer project manager can interact with the system now and can see everything that's going on, and presented to him in a dashboard, or him or her in a dashboard, which gives them the vision of what the project's doing. So that's what we wanted to get to, and this is what we started to develop in terms of proof of concepts and also prototypes of the various different technologies. So against those 5 areas, I'll just give you a flavour of what we were developing. So in the design phase, we started to look at using computer design, nothing new there, but we started to use virtual reality in a slightly more intelligent way during the design process. So for example, we started to use VR and remote streaming of 3D models during the HAZOP process within nuclear design. So that basically allowed us, for example, to walk around the rigs in a digital world to look for things like physical hazards that could occur when you're operating the rig. And one of the things we spotted in this was I'll get onto it a bit later, we actually achieved some cost savings as a result for it. During the construction phase, we employed techniques such as live streaming and used Internet of Things technologies. I'll give you some examples of this in later slides as well. For the operational side of things, we built a proof of concept of a digital twin, which brought together the CFD models that used in the design of the rig, and also dashboards and front-end system models showing how the rig operates. From a maintenance perspective, we started to develop a proof of concept of what a common data environment would be for this rig, and that an information store where we bring all the data from the asset, all the quality plans, all of the output information into one digital asset, which will then basically mirror the actual real rig in operation. And then the ultimate goal was to bring all of those things together into this common modeling environment and demonstrate that. But that's further down the line. And we haven't got any examples of that in this project yet. So I'll just give you some quick snippets of the projects and the advantages we got out of it. So in VR, we were working with University of Liverpool Virtual Engineering Centre. They supported us during the HAZOPs and during COVID. We were able to use the 3D model during the HAZOPs, which meant that gave us a much richer experience because we had to do everything over Microsoft Teams as opposed to face like you would do traditionally with paper drawings and pinned on the walls. We used VR to identify issues with the design. For example, the rig is about 4 meters tall. There's a platform at the top, which is accessed by a ladder and has a safety door, which is supposed to close behind it. Well, it was only through using the VR we noticed the door being attached the wrong way. So actually, if an operator went up to the top of the rig, they couldn't close the door behind them. So we're able to reverse it. Now, that was actually quite interesting because a colleague shared with us that a similar issue had actually occurred on a rig that was built on an active plant fairly recently. They installed the safety door the wrong way. That had to be remedied, which meant putting scaffolding up in an active area, which took weeks and cost quite a lot of money, basically. So we can show already that you can start to use digital technologies to actually correct issues that could cost you problems and delay your projects. That's VR. For digital twin, I mentioned this very briefly. I'll give you a bit more details here. So we worked with, again, University of Liverpool and also Jacobs here. We used a lot of the technology that was developed under another BEIS innovation program called NVEC, which stands for Nuclear Virtual Engineering Capability. And what we did there, we took a CFD model that was developed by NNL as part of the rig design. We developed a system model in Simulink with BEIS, and we developed that into a digital twin. So we have a dashboard, which represents all of the different sensors that occur in the actual physical rig in reality. That's all underpinned by the actual models. And then we have pressure and mass exchanging between the models of this technical demonstration. And that was what was probably the main outcome of that was just how easy that was, because very little of this had to be created from scratch, because the complex bit was the CFD model, which we had to create anyway as part of the design process. So we already had the main digital asset that we needed for this. All we needed to do was create a simple system model of the rig, which is very easy to create in MATLAB, and the dashboard. We're using all standard components and using some technology we got from other projects as well. So this activity was completed in just a few weeks of work. So, but the advantages of it are basically that we have a digital asset that connects all of the other digital assets together to create a digital twin. Very simple, potentially very effective in the future. Next bit on the common data environment, we looked at basically broadening the scope of what we've been doing under the Nuclear Virtual Engineering program to actually look at all of the potential digital assets that could be gathered from a project such as Project Faith. So we looked at things like what would we do to store CAD files, design parameters, functional specs, material specifications, safety data sheets, etc. All of the QA documentation, the risk registers, the project quality plans, the stage gate reviews, everything that you would generate in a project. We looked at seeing what would be the data architecture to actually link all this together. And we mapped out within that a set of models where we would have data and parameters for key pieces of information, which would then be shared across multiple other digital assets or documents or spreadsheets. The ability to link that to sensor data from the rig for operational parameters, and from a project's perspective, to be able to replicate this in a process of change control, representing the change control you would do in a project, for example, by creating checkpoints and branches. So for example, when we went through a design iteration, we were able to create a new checkpoint or branch to a design. And from the point of view of managing the project, then we'll be able to see how things progress. So what we did was we basically built a proof of concept of how all this would work within the project. And actually then implementing it for future rigs would be a fairly straightforward thing to do, because we understand the issues now and what's needed to make that work. And that's a step towards this common data environment, which is a step towards the common modeling environment, which is the ultimate goal. Finally, what we've got, we did some work with an SME, which was basically around Internet of Things and sensor technologies. What we did was we deployed a number of sensors on the rig to monitor it during transport, during commissioning, and also post-commissioning during operation. So we installed devices such as power voltage and current sensors on some of the power assets, temperature and humidity sensors, GPS trackers. So for example, we followed the shipment of the rig from Cameled's manufacturing facilities up to NL's Workington facility, measuring the vibrations the rig went under during the road shipment. We had strain gauges and other technology on there as well. And the whole idea with this was to make sure that from a modular construction point of view, we commissioned the rig at Cameled, we shipped it to Workington, and all we had to do then was what we call setting to work. So we had to assemble it. So unlike traditional nuclear projects where we build things in situ, setting to work in a nuclear facility took about 3 or 4 days, which the feedback we had from our facilities people was that apparently they were open-mouthed at how quickly we could actually put a nuclear something into a nuclear facility, basically, because that's traditionally that would have taken months of work on site to actually do. So that again was very successful. Going forward, this is another source of information and data which we'll be able to use as part of digital twin as well. So it wasn't just a technology that could be used during commissioning and transportation. It's something that could be used to monitor the performance of asset going forward, to see if there's any degradation in materials or performance of any of the asset, which then would affect performance. So that was quite successful as well. So just kind of summing up then, well, what have we learned from Project Faith? Well, we set out with some grand goals of seeing how we could use digital technology to address some of the big questions around the nuclear industry strategy, around saving money, reducing costs, etc. Better addressing some of the issues in terms of siloed information, handover information, etc. What we've ended up demonstrating here is a number of pieces of a puzzle, but we don't have a complete picture yet. So we've sort of got Internet of Things, but we can sort of see how that could link to digital twin, but we've not quite connected them up just yet within Faith, but we can certainly see how we can do it. Digital twin and data management, we understand how those two pieces would fit together. We sort of have VR floating around. We're not quite sure how that aligns with the others, probably less clear how that integrates into digital twin and data management, but we probably can figure it out. From an asset management point of view, we've done some work around what actually was required in terms of data acquisition and data management, but at the moment we don't really understand yet how to connect it into the digital twin. So we don't really understand the process yet, and we don't really understand the roadmap. What we've got is some bits that sort of link together and some bits that sort of not quite linking together at the moment. So if we think forward to what the future is, we need to come up with what that roadmap is. And the overall objective is around going from, if we're to go from rig 1, which is the water rig, to rig 2, which is the sodium rig, the challenges there from a conventional safety perspective are significantly higher to operate with liquid sodium than it would be to operate with water. So what we really would want to have in place is a common data environment to help us do the design of that rig, and a common modeling environment which would help us do the operational of that asset. And what we want to be able to do is, in the next phases of the project, is understand how we can link all those things together. So we don't have an answer to that yet, but what I can talk about is a bit of the motivation for wanting to do that, and the lessons learned from doing things conventionally in Project Faith. So the first one was, one of the things we noticed during the project was that the schedule shift due to communication issues. And we had a situation which developed, which our guys at NNL were basically coming up with design concepts for the rig. We would have a meeting with Camel Ed, who were designing the rig. We would agree some changes to the design. We would then go away, write a technical memo. That would go through QA. We'd issue it to Camel Ed, and then they would go away and update the design accordingly. Well, what we found was that our guys were giving the feedback. This is great. We're making lots of progress. We're getting towards the design. Everything is going great. From a Camel Ed's perspective, they were saying, these meetings are terrible. We're not making any progress. We're no nearer getting the design. We just seem to be going backwards and forwards. So what happened is that the actual process of actually getting that design agreed probably took about twice as long as we programmed for. Couldn't say at any point that we weren't making progress. It was going a lot slower than what we would like it to have done. And now, if we'd actually had that common modeling environment, the common data environment, so instead of actually going away and doing our CFD calculations in isolation, and then writing them up and producing technical memos, which went to the people who were doing the design, if they were actually able to pick it up straight from the environment, that would have sped up that process considerably, and would have reduced the length of that phase of the project by probably 50%, which, given the fact that Project Faith had a project burn rate of around £250,000 to 300,000, probably a bit more, pounds a month, is a significant cost saving if the project was fully mobilized in that phase. The second one, which was probably even better, I must be one of the only technical leads who was actually happy when we made a mistake, because I was happy because it gave me some data which underpinned the need for the digital program. And that was, we actually ordered the wrong test section. So we went through this design iteration as I described previously. We had 3 different designs. We agreed on design 3. What happened was the lead engineer issued design 2 to the manufacturer. They went away and manufactured that asset. We spotted the mistake. That mistake was corrected, and we had to order the asset again. Now, in Project Faith, that cost maybe a few tens of thousands of pounds to order the test section again. It caused a bit of embarrassment, but that was about it. Now, if that had happened in a real project, however, and in Project Faith, all we did was we just demobilized everybody. We ran the project down, and we incurred very little extra cost as a result. If it happened in a real project, you probably couldn't have done that. You probably would have had to keep all your staff mobilized. They would have sat around waiting all the months that would have taken for the new test section to come. In total, that delay probably cost us about 8 months in our schedule. Not just because of the order in the test section had to be done again, but of course, everything else going on with this global pandemic, etc. We had Brexit going on. So one time we had the bits of the rig stuck in customs. We had people stuck in different places in Europe, unable to come over to do installation and testing work. All of those circumstantial things. But if we'd actually done it right the first time, we wouldn't have had those problems. So we'll accept the 8-month delay. So 8 months, it's £250,000 a month. So basically would have increased the cost of the project by probably 50%. So now you can see what the benefits of digital would be. So if we were working off a common modeling platform, there wouldn't have been any question of sending the wrong drawings to the manufacturer, because it would be obvious which drawing was the latest one, because it would be the only one that was approved on the common modeling environment. If you have this within larger projects, of course, the cost impact of this could be even greater. And we've heard from, for example, from EDF Energy, where a not a dissimilar issue in some ways from a project's point of view effectively cost them around 10 billion euros on a major project, because they simply couldn't slow down the project while they waited to correct a mistake that was made from a supply chain, and because the communication between the supply chain and the EDF engineers was so poor because they had no common way of working together. So you can see, therefore, that there is a real driver within nuclear to get these digital technologies working, because we can make real savings on these projects. And that's the driver we have now for stitching all of those different pieces of the puzzle together. So here we go, here's the messages. We want to avoid delays, we want to avoid rework. That's the benefits from a common data environment. We realize a digital strategy, we can improve client engagement, and we can maximize that return on investment, getting rid of all these cost overruns that occur on these projects. So, summing up, what have we learned? Siloed working. We've learned that we can introduce innovation very quickly within an R&D project, so that learning can be applied more rapidly to more challenging projects. So now we know clearly what our R&D roadmap needs to be to go from rig 1, water rig, to rig 2, the sodium rig. We've given some simple real-world problems that allow us to quantify the impacts of loss of fidelity of handover in a nice sandpit project like Project Faith, where nobody got hurt, no one was impacted by any particular cost saving, because it was just almost a throwaway project in that respect. But now we can see what the real benefits are for real projects that we have in the future. And collaborative working. It's shown us the benefits of using digital technologies such as VR. It's shown what the future of common modeling environments would bring in terms of collaboration as well, to collaborate and to introduce new ideas that would make projects run better in the future. So finally, just to sum up, I'd just like to acknowledge all the different organisations that contributed to this work. So we've got GE Hitachi, who are the industrial lead, and National Nuclear Laboratory CAMA-led, who are the overall lead for Project Faith. Fraser Nash, who worked very closely with NNL on the thermal hydraulics part of the programme, Nuclear MRC, who dealt with a lot of the manufacturing of the test section, working directly with CAMA-led. Jacobs, who led up on the digital ecosystem design, the Virtual Engineering Centre, who led off at the University of Liverpool, who led off on the digital twin, also the VR aspect. 11i, who were the SME, who did all the brilliant work on the Internet of Things technology that we demonstrated in Project Faith, and then finally Sunbeam Management Solutions and Mr. Philip Isgar, who was the intelligent client digital on this project, who greatly assisted in terms of setting up that roadmap and the digital vision. And thank you for your attention. I think we'll have a Q&A session now.
Yeah, thank you very much, Dr. Bankhead. Really fascinating talk and kind of a lot of food for thought as well. One question that came to my mind is how pioneering the work is, and how the kind of models, digital twins, can be applied to so many different sectors. But obviously there's a lot to learn from the nuclear sector, because they're kind of spearheading digital twins in the world, really. How do you strategize and prioritize which data that you're actually going to kind of model and collect? Because obviously there's so many different data points you can choose from. And I guess a big part of digital twins is really kind of honing in on the most important factors. How do you approach that? I'm curious.
Well, at the moment, there's probably no systematic way to do that. I think that's one of the major challenges that we have at the moment. I mean, the best sort of advice we have is sort of almost like a rule of thumb, which is to say, well, look at the law of diminishing returns, basically, and say, well, we can acquire everything, but does that bring us any benefits? That's quite, at the moment, I don't think there's a systematic method for strategizing that. I don't think that's a problem today, though, because the digital technology isn't quite there yet. Generally speaking, that prevents us from doing something before the issue of the data becomes an issue. That's not always the case in nuclear, because of course everyone in nuclear would like to measure everything inside a nuclear reactor core during operation, but you can measure virtually nothing. Bruno's laughing, but you can measure virtually nothing because it's just sort of hazardous environment. So nuclear is possibly unique with a lot of industries in that respect, but at the same time though, even in a nuclear plant, there's so much you could gather from the system, auxiliary systems around it that you don't do because you wouldn't have the computing power to do anything with anyway. So you've still got that limitation there. And I think a lot of these strategies, the strategies need to be developed, but it's probably going to be a while before that becomes a problem, I think.
Okay, thank you. That's a really thorough answer. So I know Adolphus has his hand raised. Would you like to unmute yourself and ask a question, Adolphus?
Thank you so much, Francis. Good afternoon, Professor Bankhead. So thank you so much for your insightful discussion. And I really like, you bring up the challenges of silo working, loss of fidelity during the handover of information, as well as collaborative working. I really enjoyed how you actually raise these challenges and, talk about the solutions to solve each and every one of them. And so essentially what I wanted to ask is, like I understand when dealing with nuclear-based data, there's always an issue with security because some of these data might be sensitive. And I see, or perhaps I might have missed this, but I don't think this issue of security was actually talked about, or at least talked about much in this presentation. So I assume that you probably, like I might have missed out the link somewhere when we discussed the solution on how did we actually, sort of like get past this issue of the red tape, with security clearance when you especially want to work when do international collaboration between countries. Like, how did we actually bypass it?
Well, nuclear is probably one of the most collaborative industries worldwide in existence. In terms of fundamental basic data, for decades, going back to the 50s, we've been sharing fundamental information worldwide, even with countries we would say would be our enemies, such as Iran, China, etc. Because it's from a site of benefit. You don't want somebody to build a nuclear reactor that goes a core meltdown because you withheld some critical parameter, which would have helped them avoid it. So
yes,
there's that side of things. I mean, the security argument is an interesting one. A lot of the issues in nuclear are not because we can't share the information because it's secure. It's more that we haven't got the technology to do it. And that can often be a result of just a lack of investment, not necessarily because of some technological barrier. Okay, so, but part of that reason why there's lack of investment is because that no one's really demonstrated why you should do it.
Right.
And only through bringing out this digital roadmap and the benefits of sharing would you actually demonstrate it. I mean, for example, we have had collaborative platforms able to share data with universities, various different iterations of it, as long as I worked in the nuclear industry pretty much, which is nearly 20 years. They've all been absolutely terrible in terms of the way they worked. That's not necessarily because maybe the technology wasn't very good, or but there was always been a willingness to be able to share information, and it means, security clearance. We've got processes to do that. That's not a problem. We can do these things. It's just the willingness to do them and the willingness to invest in the technology to do it. That's it. That's the biggest barrier. Two big blocking statements in nuclear. It's unsafe and it's insecure. You want to stop anything for any reason, you say one or the other, even if the neither is true or either is true. Bruno's laughing. Yeah.
Right. No, actually, I agree with you because I see these two words being commonly used. Whenever the common excuse is either like it's not safe or it's not secure. So these are the two like big words that always come out when when we don't get what we want for our research and all that. Yeah, I agree with you on that point. And yeah, but anyway, thank you so much for your insight, Professor Bankhead. So let's leave time for my other colleagues to ask your questions. Thank you so much once again for your time.
Well, thank you.
Thank you, Adolphus. I believe there's a hand raised as well. Would you like to unmute yourself?
Yeah, thank you. I'm Denis Litskevich. I would like thank you, Mark, first of all, for the really interesting insight into the FAITH project. I was a bit updated by my colleagues on what is going on, but it was really interesting to listen from your side the full overview and the challenges you faced during the projects and the successes of success, what went good and what went wrong, and so on. That's really interesting. My question is about the common modeling environment you mentioned. Do you think we need to develop the common modeling environment, the special one, or the existing modeling environment on the basis of the high-level architecture and RTI, which is used by the VEC in particular, is good enough? Thank you.
That's an interesting one. I mean, the work that the VEC did with Jacobs and others on that platform was, I mean, it's not the only way of doing it, shall we say, and there are other off-the-shelf technologies that would do the same. What I would say is we need to use off-the-shelf technologies. What they are is probably irrelevant. And that's another important part of digital transformation. It's more important that whatever we do is open so that it can connect with somebody else's common modeling environment where we need to. One thing that doesn't work is everybody adopting the same platform, because they won't. No. They never will, and they never have. We've seen this so many times in other parts of industry. I mean, you actually look back, it's the 80s when we were building the Thorpe facility. They weren't very far away in terms of their thinking from a common modeling environment. They just didn't have the technology to create it, and they couldn't work out why they wanted it as well. I've seen proposals from 1990s for what basically would be a common modeling environment that weren't funded. You just have to make sure that every technology you put in is open enough that it can be connected to somebody else's choice of whatever technology they think is the best solution to the problem. Yeah. So I don't think we need to adopt one technology over another. We just need to make sure whatever one we use is potentially compatible with anybody else's, whether you use Microsoft or I don't know, Siemens, whatever. If you want to do a big deal with Siemens, go ahead, fill your boots, so to speak, but don't expect everybody else to do it.
Yeah, thank you.
Thank you, Dennis, for your question. Sabda, do you have a question?
I'm Sebastian, who we haven't seen for a while.
Sebastian.
Yeah. Hi, Mark. As you know, I'm writing a journal article about Project FAITH, where all of us, all of the group that are involved in this project, will be authors. And I've seen lots of interesting points in this presentation, specifically the link between the DRD project and Project FAITH. And I would like to know if basically you could send me this presentation so that I can improve the introduction for this journal article, since some points are not so clear onto where does this project fit in total. And of course, I'll be showing, once I send it to you, and at some point I'll be showing you the different results that both I and Venkat have been obtaining, both for Rig 1 and for Rig 2, where obviously you'll see that, as you mentioned before, that the main changes, the main challenges between Rig 1 and Rig 2 are basically shifting into sodium plus applying heating. So yeah, could you send it to me later?
Yeah, I'll send it to you. I'll also send you a summary, Sebastian, no problem.
Yeah.
There is some information on our website. There's not as much as we intended to do. We will be sorting that out in the next few weeks, actually. But there is a video which also gives a good overview of the and some text on our website, of Project Faith, which is quite good from an overview perspective.
Well, to be honest, compared to what was sent to you previously, I mean, you know, at the beginning of the project, we were all kind of tackling the friction factors within Project Faith, but obviously there are other things that I and Bankhead have been addressing, which are, you know, features like the velocity profiles, which, you know, are affected by the wires, and obviously the temperature profiles in the case of Rig 2. And hopefully, you know, once all the data is properly compared, I think, you know, we'll be ready to publish the journal article.
Okay, that's good to hear. Thank you.
Thanks, Sebastian. Do we have any more questions from the audience? No? Going once, going twice. Bruno, please go ahead.
Hi, Mark. First of all, thanks for the really comprehensive presentation. Yeah, that's very good. Yeah, how do we go ahead with it? That's a question for me. How do we press into the next level, into the next project? How do we make more out of it? It was a good first step.
Well, that's an interesting one. What do you mean? Where do we get the funding from? We've laid the groundwork here. I think that there needs to be a bit of a drive now from within the nuclear industry to adopt digital more. I see a lot of willingness from within various companies like SL. Have got, you know, pretty good digital strategy now. They don't really know how. I don't think they really know how to make the next step. They've got some ideas, but they've not been very tentative about them. We just need to get on with it. Really, we need to make sure that this is a centerpiece for all the projects that we do. So, I mean, yeah, it's so important. This, if we are going to successfully deliver new EMR technology, SMR technology, we have to get this right. Otherwise, we'll just overspend by 50, 60, whatever, 200% again, which nuclear industry can't cope with. Other industries just absorb the costs. It was one of the things I learned by talking to the construction industry council around BIM, and they told me that, you know, 80 to 90% of construction projects don't have a budget because the private sector, most cases, don't care. They just have a vision. They want a building and they want it to look beautiful and they want it to accommodate so many people, and it costs whatever it costs, basically. There was actually a brilliant quote from the chief financial officer of Apple, and someone asked about the Apple campus being 100% over budget, and he says, I don't recognize that figure because there was never a budget in the first place. So it can't have been 100% over budget. Whatever it cost, he was paying, they would pay for. That's all they care about. And that's the majority of construction projects. If you've had any work done into your house, you know that's true. You have an aspiration, that's not a budget. Whatever the builder tells you its costs, you only really know at the end. And that's true. Nuclear can't cope with that because
no, absolutely not. And I'm shocked about this, since I have seen, for example, numbers for the refurbishment of the central Siemens building. And I've spoken with the company who has delivered the logistics on it, and they said at the end they were 10% under budget and they were under time. So it is possible, but the point is that's very often forgotten, that when you go to these prestigious projects, then it has to look good. Nobody looks, if a nuclear power plant looks good, and nobody looks at the end, is the electricity produced nuclear or by wind or by sun? The question is, it has come out of the socket. But people are not paying for a certain product, since you cannot be proud of this product. And that is, I think, a really important thing for nuclear, why we have to go these new ways, why we have to optimize. Since to sell an Apple phone, since it's a cool Apple phone, and everybody can put it on the desk or can put it on the counter when you're at the bar, is something different than delivering electricity. And at the end, whether or nuclear, it doesn't matter. At the end, it's electricity from the socket. What is accounted for?
Yeah, absolutely. I know we haven't got much time left, Francis. I wonder if I can ask a question now, and just so everyone wants to volunteer, is that from a Risk Institute perspective, what do you guys see as the big opportunities and challenges around digital twins? Anyone would like to stick their hand up? And
I feel like there's quite a few people in the digital twins working group here. So, I mean, either Nick or maybe Enrique or Ander might be well suited to chip in here. Maybe I can single out Nick.
Yeah. I was going to ask a question and then somebody else sort of usurped the question, which is, so yeah, as Francis has singled me out, because my PhD is sort of funded by a digital twin project, although I've migrated myself away from doing anything remotely sensible, should we say. But I think the thing that's come out of it is this, and I'm trying to think of the exact phrase you use, but sort of common, sort of a modeling platform and common data platform. Is that the right? I can see nodding, so I'll go with it. Those sorts of ideas, is actually that's all that you have for a digital twin, beyond the buzzword. Essentially, that's all these people are talking about, is ways of viewing data and then sort of modeling decisions. That's, from my perspective, what they're talking about. Ander is the other one that could chip in, I guess.
Enrique's got his hand up. Yeah.
Enrique's got his hand up as well, so maybe he's had some time to think on it.
Yeah. So I see many challenges, especially I see one that is often overlooked, and it's related to the integration of the different softwares. Because when you build this digitwin, you rely on different software that model different aspects of the system. So, for example, you have something that deals with thermohydraulics, and then you have something that deals with nuclear reactions, and so on and so on. And the problem is, how do you create something that integrates all this multi-physics together, and it doesn't break with time, because eventually the software will update, and then you will have integration issues. And also you will have people who have been working on the coding are leaving, and there's some kind of loss of knowledge as well. And the people coming, they don't really know how the previous people were working. And so it's this problem of, I'm not talking about the physics, I'm talking about the coding, the software trading. And I think that's probably the main, I think it's probably the main problem, honestly. Yeah. I'm not sure if you thought about that.
Well, I'm kind of conscious that good to be saying this in a university, digital skills aren't very good. best way of describing it, really, to be honest. We don't train people anywhere near enough in digital skills, from schools through to university. It's hard, you know, we find it very difficult to recruit computer programmers because surprisingly, there aren't very many of them out there. We can't compete salary-wise with a lot of the bigger players as well, of course, so it makes it even more difficult. But digital skills is very important, particularly for scientists, and I don't think it's anywhere near good enough. I agree with you completely. I think that's probably one of the biggest barriers on this.
Yeah. So people that know physics often don't know about coding, and people who know coding often don't know about physics. So
yeah. Now there are some advantages of that, however, because probably the worst thing, and this very much happens in nuclear, is that when they are the same person and they are the only person, that's a nightmare. When you literally have your physicist and your programmers the same person, and nobody else knows what they're doing from the physics point of view or the programming point of view. That happens all the time. We've had a number of projects with customers where we've had to come in and almost rescue them from that situation, where somebody who knew everything is retiring, and they literally would have ended up with nothing if we hadn't come in, helped train several people to take over their role. It happens all the time. It's a big risk. So we have to try and find a way of separating those roles, I think. But you're right, then that creates a problem in itself. It's like, how does the scientist know how to talk to the computer programmer, and vice versa? There's lots of issues going to have to come out of that one. So yeah, not easy.
Yeah, definitely. So we have a couple more minutes. I'd like to wrap up by asking a final question, which is, I think you mentioned one mistake during the project that you made, but I'm wondering whether there's any other failures or kind of lessons learned from Project Faith, and if you could do things again, what would you have done differently?
It's a tough one because everything's been so skewed by the COVID situation, unfortunately. And that's really been the problem. I wish we did the project either 2 years later or 2 years earlier.
Sure, but even with COVID incorporated into it, how would you have done things differently with COVID being in the mix? Because I think that's quite fascinating in itself. You know, we might have similar disasters happen in the future.
I think the thing around the common data environment, something could have been created up front, which wouldn't have been a very good common data environment. But if we could have created something up front, just even if it was just a document sharing platform, we tried, but unfortunately, this is one of the lessons as well. Various different organizational ITs got in the way, so we just couldn't find a common platform that everyone could work with. If I'd done the projects again, even if that all we had was a document sharing repository, I would have had it, and that would have solved so many, you know, the problems with the rig wouldn't have happened, basically. It probably wouldn't have happened. Couldn't have guaranteed it without some document control, but I think that's one thing we would do, and that would be the very first thing we would do in Project 2.
Okay.
As a minimum, we need that sharing platform.
Okay, thank you very much. I know that Nick's actually just said that he had something very intelligent to say. So
you must say it. Then.
One more question. If that's
you must say it. You must say it.
So your conversation with Enrique sort of prompted my memory to a talk that I heard sort of right before we went into lockdown last February, in which there was a guy there who was talking. He works for a company, and I can't remember the name of the company on the top of my head, but they make components for aircraft. And what he said, his worry about digital twins is that this technology moves on, and whereas they say that they still have aircraft that they helped to build in the 1980s, and that aircraft was produced for 20 years, and therefore there are still models flying, and every now and again they get okay, we need to see the original drawings of the landing gear. And that is fine when it was built in the 80s, because there is a printed out version of it. There is a a blueprint that's been hand drawn, whereas the stuff in the 90s was designed by computer, and they then very much struggled to find it because it's been digitally stored and the files being corrupted or whatever's happened, and B, that actually the software doesn't exist anymore. And so sort of, have you thought about that problem in the sense of that? I know nuclear is a very similar thing. If you build a reactor and you expect it to last for 30 years and then it's extended lifespan again. So in what sense are you imagining this stuff as this software is still going to be able to work in 40 years time? And a sense of, as that you were saying with Enrique, the people that have wrote it have long since retired or moved on or just simply forgotten about, on line 174, there's this little bodge because it was the only thing that I could get to work and it's just stopped it being buggy. How do you envisage dealing with those sorts of issues?
Well, in a way, we've kind of solved some of those problems because of the way we've been working previously. So one of the ways, I mean, Josh, who works with in that same team as myself as well, is aware of this. We work on a lot of process models of plants, and how we did it was we store all of the critical parameters and equations and write the models in such a way that they were translatable. So we can take a model from the 80s and translate it into a piece of software for now, basically. And we do this from time to time, where we kind of revisit legacy models. And that's the only way to do it. You need to make sure you store the information in multiple places. So you can, if necessary, you can recreate your CAD. I mean, the CAD people have struggled with this with years. Converting CAD geometries is an absolute nightmare. You can't do it, basically. So you have to store the actual parameters separately so you can actually recreate it. And there may be other technologies you could use. You could use things like 3D scanning, for example, to recreate your drawings. But there's no way around this, unfortunately. And you may make choices on software with good intentions, but only to find that the company exactly goes out to bust or just moves on, and you just can't use the same software anymore. Then you basically have to recreate it again. And that's the only way, I'm afraid, to do this. And maybe in the future there'll be better technologies to help us to do this. I don't know. I'm sure our guys, colleagues in some of our facilities in Cumbria have got quite used to supporting some rather old computer systems because they're basically baked into the control system of the plant. And you just can't remove them without basically rewriting the entire safety case of the plant. So, you've got to deal with that, and got to deal with the data as best you can, basically. But I think that's the only way, is make sure you've got enough information to recreate it again. That's it.
Just to comment on this, you're never sure that you have access to information, for example, in the 80s. I remember when I came to NNL, I was asked about the fuel assembly, test fuel assembly, which was in one of the NNL premises, which was delivered by Siemens at this time. And I tried to use all my contacts into Siemens. And I think I got exactly the right person to search for. And he was really, really frustrated. He was one of the top guys. And he said, you can't believe that obviously you have delivered me the data, which should have made it me easy to identify the data on the system, but I can't find it. It is simply impossible. Yeah. Even in nuclear, this happens. You can't avoid it. No matter if it's on paper, it would have been on paper, or if it's digital, you have to live with this, and you have to find bug fixes, or you have to make a decision. At this time, we made the decision, okay, let's drill a hole into. We have done our best to acquire as much information as possible. We know if somebody would try it 10 years later, the chance will definitely not get better. So then you have to make a decision. That's the job of an engineer. Make a decision on a incomplete data set. that this is what you have to do. That's very often when you're in management, you don't have all the data to make a perfect decision. You have to stand it, you have to minimize the risk, you have to try your best, and at the end you make a decision. That's hard. That's a hard version of life, but that is what you have to do.
Yeah, agreed. All we can do is help.
Amen. Yeah, amen.
I was just going to say, I'm just, I know, closing up. So thanks for listening and everything. If anyone wants to reach out to discuss digital twins or digital or anything else, just please get in touch with myself and Josh. We're very happy to hear about the sort of work you're doing at Liverpool. As I say, in an ideal world, would have come down and would have been able to have a chat about this over coffee. But as I said, you know, these Zoom systems, they're pretty rubbish, really, aren't they? So a long way to go. So it would be great to have a catch up with you guys to hear about what you're doing and how your research can help, and any ideas you might have in the future. You know, there's tons of stuff. I did think of something else actually we'd love to do. I'd love to get a psychologist working on the next project.
Yeah,
because understanding how people interact with data, I think, is going to be more important than anything. And it's very easy to redraw organizational charts around having digital systems. Putting it into practice, I suspect, is going to be a lot harder.
Yeah, most definitely. If you'd like, I can share your email in the chat, Mark, and anyone that has any questions, they can follow up with you.
Yeah, of course.
Okay, so thank you very much, everyone, for attending.
Last comment to what Enrique mentioned before.
If you must, Sebastian, we're about to finish, but go ahead.
Well, it's just that, you know, a coupling software environment is already being, you know, developed, or, you know, it's currently being developed at the University of Liverpool, but for LWRs. So in reality, the difference between LWRs and SFRs in this case would just be changing the material properties and the correlations that are being used to model different phenomena. It is inevitable that in the end, all of the codes will be coupled, because as you mentioned, there's some codes that deal with the neutronics and hence the nuclear reactions, and others that deal with the heat and mass transfer and hence the thermohydraulics. But it is impossible to generate a thermohydraulics distribution without an input, a power distribution, which in an experiment, of course, would come from, let's say, probably heater rods, but in real life and in a real SFR, it will come from the actual fuel pins, the actual neutronics codes. And as well, the thermohydraulics distributions will have an impact on the nuclear reactions through the feedback. So in the end, the coupling will always take place. And in reality, shifting from one type of reactor to the other is just changing correlations and the models. But the principles of coupling are very similar. Also, there are other types of codes being involved, such as risk and uncertainty codes, as well as fuel performance, which deal with the fuel integrity, for example, of the fuel. So in the end, it's a problem that is currently being tackled, but it's just being tackled for a different problem. But in the end, extrapolating, conclusions from one specific, from a certain specific work to another problem is, I don't think it will be such a challenge in the end.
Well, I don't necessarily agree, because what you've described there is a few things coupled together. It'd be quite a different thing to couple a few hundred or a few thousand things together, and that's where we're heading. So it will get more complicated, and then also many of the different types of information that we couple together are not so easily represented in correlations as well. So that's another thing we'd have to think about. So it depends on how you see the scale of the problem, Sebastian. I think it could, it will be a big problem when you do it at scale. Very nice when you can do it between two codes. Let's see someone, nobody's really done it for 3. Never mind 4. Right. Yeah, so there you go. Okay.
Thank you. Let's respect our speaker's time and wrap up. So thank you very much, Dr. Mark Bankhead. I'm sure I speak on behalf of everyone. It was really fascinating talk and engaging discussion. So hopefully we can have you in Liverpool in person sometime soon. And thank you to all attendees for their great questions and for coming along.
Yeah, maybe 2022, eh? Yeah.
We'll see, hopefully sooner. All right.
All right. Thank you, everyone.
See you later. Thank you, everyone.
Thank you, everyone.
See
Thank
you.
you.
Bye.